Now that we have some idea what's happening under the hood, let's return back to the fourth step in our model's execution. We see that it's actually made up of two parts. First, we computed the gradient of the loss function, categorical cross entropy, with regard to the parameters of the network. This is called the backward pass. Second, we adjusted the parameters a little in the direction opposite to the gradient, thus lowering the loss on the batch by a small amount. Taken together, this is gradient-based optimization. Let's go back to this diagram we used to understand the process. Remember, our goal is to find the minimum of the original loss function. Since we operate gradient descent in a high-dimensional space, every weight coefficient in a neural network is a free dimension in the space. There may be millions of parameters. Our very basic neural network has over 400,000 dimensions. The concept is basically the same as our simple diagram, it's just scaled up to n-dimensional space. Let's return to an example I presented in the first unit. I said that when fitting a simple y described by x linear model as presented here, all we're trying to do is minimize the distance between each individual data point and the model. In this case, the model is a straight line. At the point where we draw a model with the least sum of the squared residuals, we've achieved the optimal model. That's not a far cry from what we're trying to do here. We're just going about reducing some function in a manner appropriate to the complexity of the data. Okay, so let's move on to the last fundamental component of deep learning, backpropagation. So far, we've just imagined that the loss function is dependent on a single weight matrix. Of course, in reality, a neural network's loss function consists of many tensor operations chained together, each of them having a simple known derivative. For example, this neural network is composed of three tensor operations, A, B, and C, each carrying its own weight matrix. Calculus has a very handy way to tie all these functions together with the chain rule. Let's look at a more intuitive example. Imagine we have a function nested inside another function, like x squared nested inside the sine function, which I plotted here. The derivative, which we're going to write using another standard format, is described by the chain rule as such. So we have one function, g of x, which is x squared, nested inside another function, which means we have f of g, that's the sine function. We already saw the derivatives of each of these individual functions in an earlier module. The derivative of sine is the cosine, and the derivative of x squared is 2x. The chain rule tells us how to put this all together. The derivative of the nested function is the cosine of g of x times 2x. And if we replace f of x with x squared, we get the full function of the derivative of the nested function, which I've drawn here. Pretty neat, right? So when we see a larger network, backpropagation means we use the chain rule to calculate all the derivatives as parameters in one giant loss function. Taken together, gradient-based optimization and backpropagation are the two secret ingredients of the deep learning secret sauce. It's difficult to grasp them fully without getting into the details of calculus and the equations, but even without that expertise, we should at least appreciate what's happening under the hood. Remember, you don't need to build a car from scratch to use it, or to repair it, or to even improve it. The whole point of Keras is to bring deep learning frameworks like TensorFlow to a wider audience of statisticians and data scientists. Now that we've seen our full deep learning workflow in detail, let's wrap up this chapter by discussing some basic ways in which we can evaluate our model's performance.